Okay, good morning. I will start talking about regression and regularized regression in the first part of my lecture. And as I said before, in the second part I will talk about um, classification. So when talking about regression, a good starting point is a linear regression, which is the simplest approach in regression. Linear regression. So we want to fit certain data uh, um, which is plot here in terms of an input variable x and an output variable y, and the data are just points in this diagram, and we want to actually find the best linear fit to these points. Now we may have possibly more input variables per sample. Every point here represents a sample. So we actually need a matrix of input variables. So this matrix has dimensions n times p, where n is the number of samples in our data set. So this is the number of points here. And then p is the number of variables, which means how many dimensions our input space has. The elements of this matrix will be denoted by xij. We have also the output, and the output is a vector of n components, 1, y2, yn, so one component per sample. We will also use at some point a notation in terms of the columns of the matrix X. So the columns will be denoted by an X with a bar. Yes, for instance, column J is this vector here, is the input variable for sample 1, column J, input variable for sample 2, column J, and so on until the input variable for sample n and column J. So you see that this is a vector of length n. If I do not put a bar, I will be meaning just a row of the input matrix, of course represented here as a column vector. So it will be the input variable for sample I and column 1, here same sample I and column 2, until sample I and column P. So this is then this represents our column space, this is our row space. Yes, so you can actually write the matrix as a collection of columns, x1, x2, up to xp, or as a collection of rows in this using these variables here that we have to transpose, row 1, row 2, until row n. All of them transpose. Okay, that's enough for notation for starting. Then the next point is finding the best linear model. So basically we will make predictions by building a linear model. That means we have our input matrix and we multiply this by a vector of coefficients. This vector of coefficients will be like I write it here, b1, b2, bp. Yes, so this will correspond to a hyperplane in the space in the column space of the matrix X. So one way to find the optimal parameters of the model is just to optimize the residual sum of squares. The residual sum of squares is defined in this way with the L2 norm, y minus x beta square, and we can write this actually in a more convenient way for taking the gradient that we need to do in a moment, like this: 1 minus x beta transpose times y minus x beta. So in order to find the optimal beta of that which minimizes the residual sum of squares, we have to actually calculate the gradient with respect to the variable beta and equate this to 0. Yes, when you do that, this is an exercise for you. You will see that the gradient is equal to minus 2 e transpose x plus 2 beta transpose x, and we equate this to 0. When you equate this to 0, you will find that you need to solve the following thing. Now we transpose the whole expression and we get this: xtx beta must be equal to xty. Okay, then we wish to solve for beta, so to do that we have to invert this matrix. This is a matrix of dimension p times p. So then beta will be equal to the x transpose x inverse times x transpose times y. So let me note a few important things about this solution. So this will be this may look a bit complicated. You see here the y is a column vector, the vector of outputs. This is data that we get from our training data. Then this will be we'll have here matrix multiplications and inversions, but one important thing to know is that this is a vector of dimension p times n, so the multiplication here will be just let me think, it will be a vector of length p, and this is a p times p matrix. So what you get here just is a vector of dimension p that are our parameters. This brings us to the next thing that is interesting. Let me copy this expression and bring it to the next slide. Like that. So remember that we want to actually work with a linear model, so the parameter that we found here corresponds to the following model that tells that our predictions are equal to x times b. Now we can replace b here, beta here, by the expression that we have there. Yeah. So if we do that, we get the following expression. This is x times xt x inverse x transpose y. Now you see that this expression is quite interesting. We have here our predictions y, and here we have our output data y, and in between we have a matrix. So this matrix has a name, and it's called the hat matrix. This is the reason is the funny fact that it puts a hat to the y. Yeah, so you see how standard is this notation of putting a hat that this matrix has a name according to that. So and this matrix is actually interesting because it's a projector. You can find that this is equal to h squared. So if we applied the hat matrix another time, it will actually give the same result. So it is a projector, and this brings us to a representation, a graphical representation of a linear regression that has to do with a projection. One can show actually that if one plots, let's now consider the following case, that we have three samples, yes, and we have two variables. So in the column space, we will be able to plot this the vectors corresponding to the columns of the input matrix. So this is actually our column space, and you know that our predictions written in this way here, let me write it here, A prediction can be also be written like this: is beta 1 x1 plus beta 2 x2. This means that our predictions live in this subspace spanned by the vectors corresponding to the columns of the input matrix. However, our output data, yes, is just a vector, a general vector with 3 dimensions, because we are in n equal to 3. Yes, this is y. However, our predictions will live there. So what you find is that this projection operator is an orthogonal projector operator. You are able to show in principle that this, if you apply h to y, you will get a projection, an orthogonal projection on the column space. So this is y hat, and this is orthogonal. Yes, so this is actually quite interesting, and also brings us the first drawback of linear regression. What happens, for instance, if these columns x1 and x2 are almost collinear? Suppose that instead of having x1 here, we had it, I will paint with other color so we do not get confused. Suppose that instead of having x1 here, our x1 vector would have been like something like this, almost collinear to x2. It means that a certain projection on this subspace can be represented by a linear combination of this x1, x2, but it can happen that we have a large value of beta 1 that is basically cancelled by a large negative value in beta 2. Because if I basically a certain vector here can be expressed like a large vector along xy, x1 minus a large vector along x2. Yes. So this the fact that you can represent any vector as a difference of these two vectors brings great instabilities in the linear regression method when you have vectors that are almost collinear. This is one of the problems. Another problem that I want to indicate now is has to do with the matrix xtx that we have to invert. This matrix is of dimension p. You know, if we want to be able to invert this matrix, this must be of full rank. Full rank means that the rank of the matrix should be of dimension. The rank of the matrix should, the rank of the matrix xtx should be equal to p. Yes, but this can only be obtained if n is larger or equal to p. Yes, whenever we have n smaller, if n is smaller than p, then the rank of the matrix X itself will be n or less, and we cannot have the rank of the matrix xtx equal to p. Therefore, this brings quite a strong limitation on the problems that we can actually deal with, because it means that we always need to have more data than input variables. So this is a problem. Therefore, we actually need to use regularization. So this is where regularization comes in, and it solves both problems at the same time. So it will solve the problem of linear dependencies in the column space of the input matrix, and it will also solve the problem that we cannot treat training sets with more parameters than data points. So let's now start with the simplest regularization, which is called ridge regression. So in ridge regression, we will solve the following loss function. This is the residual sum of squares first, as we had before, y minus x beta plus lambda beta square. So let's write it with a bit different notation, as we did before, that is convenient for calculating gradients. Y minus x beta transpose y minus x beta plus lambda beta tb. So let's justify a bit why we are writing that. So you see that this we want to minimize this expression. So this actually imposes a penalization on large values of the coefficients beta. We saw that when we have collinearities, we could have large instabilities because there could be some large values of the parameters, which is an artifact due to the collinearity. So we want to somehow penalize such values and bring them to more equal and smaller numbers. So this can be achieved by this sort of penalization. And then let's see how it works in more concrete terms. So we will calculate the optimal coefficient by calculating the gradient and equating it to 0. So if we calculate the gradient here, let me see. We will have minus 2 y transpose x plus 2 beta transpose x plus 2 lambda beta transpose. Yes, and we want to equate this to 0. If you do that, this is also an exercise, what you will find is something similar to what we had before. We will find that the optimal parameter for ridge regression is something like this: xtx minus lambda, the same lambda here, and the identity matrix inverse xty. You see that this is quite similar to what we had before. Before we had, for linear regression, we had that the solution was xtx inverse xty. So the main difference now is in this term here. So this was historically, ridge regression will start just by putting this term by hand here. Now we justify it by putting this penalization, but so okay, then this is called a ridge term, and what it makes to this matrix is making it definite positive, and it is then invertible even if n is smaller than p, and even if there are collinearities. So this solves the problems that we had before. Now let me see what I wanted to say about ridge regression. Yes. So now there is a nice graphical representation of this because this is a Lagrangian, so we can also write this problem as a constraint optimization. Yes. What about the constraint related optimization? So we will see this in the next slide. We can actually obtain the ridge regression solution by considering this loss function, just the residual sum of squares. Yes, and then we put just a constraint on our parameters beta square less or equal to some number t. So we will see that in that case, let's see how the solutions look like in this in the space of coefficients beta. So here this axis will represent, we will consider a case with two with two input parameters. So we have here beta 1 and beta 2, yes. And here we have we will have the optimal solution for for the unconstrained problem. If we do not have this, we'll have some optimal somewhere, and then there will be iso values of this residual sum of squares. So since it's a quadratic, this will be like ellipsoids like that. Let me see, this is a bit hard to plot. I hope it's not so badly plot. Okay. Then this represents just a circle, yes, of radius square root of t, and then we can plot this constraint. The constraint will be something like this. Let me try to, I want to just plot the tangent there, okay, more or less tangential. So this would be the constraint. So we want solutions. This region is actually the constraint, beta square less than t, and these are the values of constant residual sum of a square. Yes, so these are these values. So the solution will be found for a point like that. For instance, because if we are here, we are, yes, closer to the minimum, but we are not. Let me see. If we are here, yes, we are closer to the minimum, but the problem is that we are not satisfying the constraint, this constraint. If we are at some point there, yes, we satisfy the constraint, but we can actually go to smaller values. So a point like this will be the actual solution, and this we can see that in general the solution will have components which are different from 0 for all components of the vector b. So this means that we will obtain almost always quite dense solutions. So this is not good if you have a huge number of parameters and you would like to subtract some number of relevant parameters for the model. This will always give you a huge number of parameters. So what we want to find out is ways of producing sparsity in the solution. Sparsity means that we would like that many of those parameters are exactly 0. One way of achieving that is using a different sort of regularization that is called L1 regularization. So in that case we have the following loss function. We have again the residual sum of squares, y minus x beta square, plus now we have just the L1 norm of the coefficients. So we have here 1, where the L1 norm is just the sum of the module for all the coefficients. Shape here. Yes. So in that case, now I will plot how it looks like in the constraint case. In the constraint case, we just optimize this part, applying this constraint. Basically, the constraint would be now saying that beta, the L1 norm is smaller than certain number. Yes. So let's see how it looks like. The constraint is now the constraint will be now something like this. Let me plot here this is beta 1, this is beta 2, and now the constraint would be will look like a diamond. If you actually plot this constraint, you will get something like this. And now, okay, the solution of this unconstrained problem would be something like there. Yes, let me put it closer. Then we have we will have the iso values of the residual sum of a square. Yeah, and there will be one case in which we touch the constraint, here. So as before, we have this. We want that the solution is inside this diamond. So the best way is when we actually touch this corner here. This would be the solution that both fulfills the constraint and optimizes the residual sum of squares. So that is the closest possible to that center. So this solution is qualitatively different from the previous one in the sense that here we have beta 1 is different from 0, but beta 2 is exactly 0. So when we use this sort of optimization, we will have in general many parameters that are exactly 0, depending of course on the strength of the optimization and the position of the solution here. So this is quite convenient if we want to have sparse models that are more interpretable. So now I will stop talking a bit about the regularization in this sense, but we want to now also look at the kernel-rich regression. So the kernel-rich regression is a quite interesting method that is a different way of looking at the rich regression, which brings up a generalization of the problem to many more dimensions at a very low computational cost. So let's see what we mean. We just start with the usual loss function for rich regression. Let's write it again. So we have the loss function is so I will write the title for this. We will now talk about kernel rich regression. Yes, so we start with the following loss function that is more or less what we had before, but I will write it in a different way now using the row space. Yes, vectors in row space. It's not much of a mystery, just that I will put here. Look, instead of putting the L2 norm or something like that, I write it in this way. So we have this plus our L2 norm. So it's the same as without the word kernel. This is like that's exactly the same as rich regression. So the word here kernel will have to do with a different way of actually calculating the optimization on one side. So what we will do is to use something that is called Lagrange duality to solve this optimization problem, and start by defining some auxiliary variables. These auxiliary variables, I will write it here like set I equal to yi minus xi transpose beta. So these are my variables set I. Yes, and then this Lagrangian, I will start calling it Lagrangian, will depend not only on beta, but we will say that, okay, set I are independent variables now. Yes, we say that this will be independent variables, and we'll call it set and beta. And this can be actually written here. I put an arbitrary factor that will be helpful later. This will be the vector set transpose set. So this is the L2 norm for the set vector plus lambda over 2. Yes, the factor 2 here is doesn't modify the result. It's just for convenience. Beta transpose beta. Yes. But now, of course, now I treat here set as an independent variable of beta, but it's not independent actually. So we have to put a constraint. Yes, so we will have to minimize our Lagrangian set beta with respect to zeta, set and beta independently, but constrain or subject to having set I equal to yi minus xi transpose beta. So basically this constraint here, yes? So let's bring this to the next slide. Here. So we have this now. So now you see we have a constraint optimization, but using Lagrange multipliers, yes, using Lagrange multipliers, we can turn this constraint optimization to again an unconstrained optimization again. So what we will do is to put some Lagrange multipliers that we will call alpha I, yes, and we will write the following Lagrangian that is now corresponding to an unconstrained problem, yes. So here this Lagrangian will depend now on these Lagrange multipliers, on Z and on beta, yes. This will be equal to 1 over Z, 1 over 2 Z transpose Z plus lambda over 2 beta transpose beta, yes. Now we apply the constraint here in the Lagrangian. We account for that constraint. Then this will be the product of the Lagrange multipliers times our previous constraint, xi beta minus yi minus the zi. Yeah. So this is the Lagrangian that we obtain after defining these Lagrange multipliers. And in the context of Lagrange duality, yes, I will not explain this now because it would be quite lengthy, but if you like to find out by yourself, look into these keywords or just ask me afterwards on at some point Lagrange duality. So to solve this problem, what we have to actually do is to solve a minimax optimization. In this minimax optimization, what we do is that recognize that the solution of this Lagrange duality is calculating the maximum with respect to the Lagrange multiplier of the minimum with respect to the Lagrange multiplier of the auxiliary variable set and the parameters beta of our Lagrangian alpha set beta. So we have to actually solve this problem. It is actually not so difficult and we can do it. So again I will copy this thing to the next slide. Okay, it's not perfect, but just as a reminder. What we do first is the inner minimization. We will start with this. So if we want to minimize with Z and B, so you know we have to first calculate this equal to 0, and then also calculate this with respect to beta equal to 0. Yes, if we do in that way, what we get is a couple of equations. You can do it by yourself also. Is that Zi minus alpha I is equal to 0, or what is the same, that the Zi's will be equal to the alpha i's, and on the other side, from the second equation, I will just put the solution here. We find that beta is equal to minus 1 over lambda times the sum on I from 1 to n of alpha I xi. Yes, so now we substitute these two expressions in our Lagrangian there, here. You see now that we will not have any more the variables z and beta, but we will just have alpha everywhere and x. Then we will be able then to perform the maximization with alpha. Yes, because we will have only alpha there. So This you can also try out what is the result after substitution. In here, let me see if I find the in my notes. Where do I have it? Yes, some important thing before continuing, before making the replacement. We have now this solution for beta, and we had that our predictions are equal to our predictions for some data point is x transpose times beta. So then this can be written, if you use this solution, as 1 over lambda times the summation of from 1 to n of alpha I times xt times xi. So this is actually quite interesting, yes, and we can advance already why this is called kernel regression. So this is a scalar product of two vectors, and we can define this as a kernel, as a function that we call kernel. Yes, xi equal to x times xi, or with the notation that we are using, could be x transpose xi. Yes. So this is we will see that this is actually a very interesting way of writing things. But let me now write this using the expression for the kernel, and I will use a different color because I want that it stands out for later. So now we have that our prediction y is equal to minus 1 over lambda times the sum on yi from 1 to n of alpha I, and now the kernel between x and xi. So you see it's a linear combination of kernel functions. Yeah. Okay, now let's continue by coming back to the original problem where we wanted to replace the solutions for z and beta on the original Lagrangian. Yes, and to solve the minimax problems. What you will find out, this is also an exercise. Let me put it that way. What you will find out, this can be an exercise, is the following. You will end up solving the maximization of alpha, the minimization with set beta L is actually equal to the maximization with alpha, or something that depends only on alpha. Yeah? Minus 1/2. Now we have the sum from I equal 1 to n of alpha E squared minus 1 over 2 lambda, then the sum on I on j of alpha I, alpha j, and now let me use the kernel. With the kernel now we are now just hiding the scalar product, what could be something else, xi, xj, minus the summation on I 1 to n of alpha I yi. You see that this is now a quadratic problem in alpha that can be actually solved quite easily. Also, there is an analytical solution for this. By the way, we can also define a kernel matrix Kij equal to the kernel of xi, xj. So this matrix, this kernel matrix will be useful because now we can write the minimax problem like this: max alpha min set beta of the Lagrangian is equal to the maximization with respect to alpha of minus 1/2 alpha transpose alpha minus 1 over 2 lambda alpha transpose, now the kernel matrix alpha, plus, minus alpha transpose y. So this is quite a nice expression that we arrive after having using this dual after having solved the dual problem. Okay, so the solution to this quadratic equation is quadratic optimization is quite easy, and is you can actually find by yourself that it is equal to lambda times k minus lambda I inverse y. So again, a rich regression term. So this is indeed is equivalent to what we had before for the normal ridge regression, but it is written in a much nicer way, which is very compelling. So because the solution only both the optimization problem and the predictions make use only of kernel functions. So you do not need to actually know the whole set of features of your input variables, but just the scalar product between them. This will be useful in the context of a feature expansion of a basis expansion of your input vectors. Yes, if instead of if we enlarge our feature space in this way, by instead of having the variables h, we have some certain set of functions h of x. So suppose this in this way. So you have xi1, xi2. Now suppose that you have here a set of vectors x1, xi2, xi1 square, xi2 square, xi1 times xi2, and so on. You can make a polynomial expansion if you like, or there are other things to do. But I will explain a bit more about this in the next part of my lecture. So for the moment, let's keep it like that. And also let me point out to an exercise where you can show that the previous solution is actually equivalent to that one. We had previously that y is xtb is equal to with beta equal to xtx minus lambda I inverse xty. But now, what we have now? We have y is equal to minus 1 over lambda. Now the sum of these kernels from 1 to n, alpha I, the kernel between x and xi, and now we have this alpha, the vector of alphas will be equal to lambda times k minus lambda I inverse y. So I'll leave you as an exercise to find what is the difference, if any, between these solutions. Okay, then we will go to some minutes of questions and discussion, and then we will pass to the case of classification in the next part of the talk.